So I'm very happy to be talking here. And yes, this is a talk about the crossing number of links. And really, this is a talk about the computational problems that arise from knot theory. So this will be based on joint work with Marcus Schaefer and Eric Sedgwick, who are both at DePaul University in Chicago. And well, the starting point of the talk is that knots have been annoying people for a long time. And here we see a picture of Alexander the Great, who came upon the famous Gordian knot. The legend is that he came into the city of Gordia, where there was a very annoying knot. And the legend says that whoever would manage to untie the knot could conquer Asia. And Alexander tried very hard, and he never succeeded. But at some point, he decided to raise his sword and cut the knot, and he conquered Asia. So I guess the question that I want to ask is whether nowadays with computers, we're better at these kind of problems than Alexander the Great. And the answer is not really, but it's pretty hard to figure out. So let's start. And before saying anything, I would like to say that this is aimed to be a very elementary talk. If you don't know anything about knot theory, you should not be lost. And so if you're lost, then you should feel free to ask questions because I hope not to use anything technical. So what is a knot? A knot, it's a nice map from S1 to R3. So it's a closed curve that is embedded in ambient space R3. So for example, here we have a very nice knot, which is what is called the trivial knot. The trivial knot is a knot that is as trivial as you could find. And we say that two knots are equivalent if one can deform continuously one knot into the other one. So for example, here we have a second knot. So technically, it's not the same embedding of S1 into R3, but obviously one can flip the monogon here in three-dimensional space, likewise here, and we go from this one to this one. So these two knots are equivalent. Here we've got a different knot, and this one, no matter how hard you try, you will never succeed in untangling it, in untying it to make it into the trivial knot. So this one is a non-trivial knot, but already you should be aware that it's not obvious that it's a non-trivial knot. And really, it's not obvious that there exists any non-trivial knot at all. And perhaps this is one of the starting things when you're coming from combinatorics, which is that the very first definition entails some non-obviousness. Nothing can easily be checked by a naive algorithm in finite time, which is very much unlike properties in graph theory, for example, where when the graph is small, you can always brute force any kind of problem. And in particular, here, we've got a third knot. This one, I think, was found by Haken. And it looks like a big mess, but it turns out that it's actually a trivial knot. So you can untangle it. There's a nice sequence of moves in three-dimensional space to go from the last knot to the left one. And clearly, it's not obvious that it is the case. So this is an illustration of the problems from knot theory. Things are not obvious, and they're also not obvious to prove. Now, we want to talk about computational problems. So we want things to be more discrete. And a nice way to think about knots in a discrete way is via knot diagrams. So a knot diagram, what is it? Well, it's simply a 2D projection of a knot, where at every vertex, you write which strand goes above and which strand goes below. So basically, that's a 4-valent graph. And at each vertex, you write which of the strands is above and which is below. And here we have the same pictures, because obviously these were diagrams. That's how we represent naturally knots. And so basically giving a knot to a computer is the same as giving it a planar 4-valent graph with a few decorations at the vertices. And the crossing number of a knot, it's the definition one would expect. It's over all the possible knot diagrams for knots, the one with the minimum number of crossings. So for example, the crossing number of the unknot on the left, that's 0 because there's no crossing. And the crossing number of the trefoil, which is the knot in the middle, that's 3. But once again, I have not proved it to you because proving that already entails proving that the trefoil knot is not equivalent to the trivial knot. So as before, there's some subtleties to these definitions. And one thing that is very convenient about knot diagrams is that one can think about them, one can figure out equivalence of knots in a very combinatorial way compared to the definition that was on the previous slide, which is moving things around in 3D. And that's the theorem of Reidemeister. He proved that if I give you any two knot diagrams that correspond to the same knot, well, you can go from one diagram to the other one by just using this a finite number of the moves that are pictured below. So here, for example, we can see the first move. If I do twice the first move, then I can untie these two monogones and go from this knot to that knot. And there are three moves like that. One is when you've got a bigone, and one is when you've got a triangle, and you can basically flip this triangle. So basically what this theorem tells us is that this problem of equivalence, in a sense, it's very combinatorial. It's just a matter of testing whether you can connect two diagrams with a finite number of very combinatorial moves. The issue is that, well, in the theorem, there's no bound on the number of moves. So there's nothing really practical coming from this definition by itself. And before going into the heart of the matter, I will also introduce links because we will be dealing with them in this talk. So a link, basically, it's multiple knots. So for example, here we have what is called the unlink. It's just two unknots that are laid side by side. And here we've got another link, which is two unknots, but they're put in R3 in a way that one is linked to the other one. So even with unknots, you can make non-trivial links. Then the equivalence of links, that's the same definition as for knots. They're equivalent if you can deform them in R3, which is what one would expect. And similarly, there's a theorem of Reidemeister that goes with links that tells you that two links are equivalent if and only if there's a finite number of combinatorial moves relating them. And on the right here, we've got a picture of what is called the Borromean rings, which has this peculiarity that if you look at any pair of the knots here, for example, the top left one and the top right one, if you look only at these two things, you can pull them apart. So together they're unlinked, but the third one locks them in. So these examples show that even with only unknots, basically, you can create some complexity. You can create some very non-trivial things, and this will be important in our story. Now, there is one thing that is good about links. So from any sensible perspective, links are more complicated than knots, but that's actually good because when objects are more complicated, then it's easier to prove that they're complicated. And one way to view this here is that while it was not obvious that there were non-trivial knots, it is obvious that there are non-trivial links. And the reason for that is that because there's a very easy invariant for links, which is the linking number. What is it? It's what is pictured here. If you take two components of a link, you orient them arbitrarily, and then you count the crossings as pictured here. Some of them with a plus, some of them with a minus, and you sum this. And this gives you the linking number between two components of a link. And it's very easy to prove that this is actually a topological invariant. So here it's only defined with respect to a diagram. But when you have two different diagrams of the same link, you will get the same values of the linking number. And so in particular, this tells you that whenever I give you a link where these linking numbers are non-zero, the link cannot be trivial. And here it's the case for the link in the middle. If you compute this linking number, you will see that the two components are linked. And so that the middle link is not equivalent to the left one. Of course, it doesn't tell the whole story. Sometimes you will have things that have linking number 0 and are non-trivial. So there's a picture on the top right, as we saw, and there's a different picture at the bottom right here. That's something that is called the Whitehead link. If you apply the formulas and compute the linking number between the red and the blue curve, you will see that this is 0, and you can also prove that this link is non-trivial. All right, so these are the main players of our story, and this is a talk about the crossing number. So as we said, the crossing number, it's a minimum number of crossings in a diagram. So the question is exactly that. I give you a diagram, and can you tell me whether the crossing number is at most k? And the main theorem in our paper is that this thing is NP-hard. This problem is NP-hard. Now, I would say if somebody was presenting this result, I would not be really surprised. The first reaction is, well, of course it's NP-hard. Basically, any problem with crossing numbers for graphs is already NP-hard. And you would not expect this to be any different here. But so I would like to answer two things. The first one is that, well, maybe it's expected that it's NP-hard, but it's not that obvious to prove it. And one counterpoint is that we are able to prove it for links, but if you restrict to knots, so that means if it's with a single connected component, then I don't know how to make the proof work. So maybe you can try to figure it out during the talk and understand where the proof breaks. And another point, which I think is more important, is that actually anything in knot theory is pretty hard to prove, and in particular for complexity results. So there are very few known complexity results, both upper bounds and lower bounds in knot theory. And so basically the situation is very different from what you get if you're used to combinatorics or graph theory. In graph theory, any problem basically is either polynomial or NP-hard, except for a couple of exceptions, which everybody knows. While in knot theory, basically, this is really not the case. Everything is wide open. And this is why I think it's interesting, because as a computer scientist, we can hope to make progress, and it's a different way of looking at knots compared to what topologists have been doing for the past maybe 100 years or 200 years. So before talking about crossing numbers, I'd like to show you a bit what is known about these complexity problems for knots. And really, the first complexity problem we can think of is a knot recognition. So I give you a knot and I want to know, well, is that the trivial knot? And as I said, well, it's already not obvious to figure out how to do it in finite time. And the first algorithm dates back to Haken in '61. And the current state of the art is that this problem is both in NP and co-NP. And one way to, let's say, easily see that it's in NP is that if a knot is trivial, there is a sequence of n to the 11 rider master moves, bringing it to the trivial diagram. And that's a somewhat recent result of Lakenby. So that's your NP certificate. If you give me this sequence of n to the 11 moves, I can easily verify that the knot is trivial. And as one can guess from this n to the 11, the proof is very intricate. That's something non-trivial. And similarly, the co-NP certificate, it requires some work. So this is really not obvious anything about this. And no lower bound is known. So that's one of the few problems that are in NP and co-NP, and it's unknown whether they're NP. And I remember that last week in this seminar, there was a talk about search problems in PPA, PPAD, PLS. And one can think of this maybe in a similar way. Like here, for a problem that is in NP and co-NP, there's a polynomial space that contains either a certificate that is trivial or a certificate that is non-trivial. And then one can search this space. And so maybe one can hope to prove some results like PPA completeness or PPAD completeness or something like that, which would probably rule out a polynomial time algorithm for that. But if I had to bet, I would bet that the problem is actually polynomial. So I would not spend too much time thinking about this. But already, so even the most basic question in knot theory is not completely classified complexity-wise. And if one just takes a slightly different variant, which is now you take two knots and you ask whether the first one is equivalent to the second one, the situation is much more intricate. So it's even harder to prove that this problem is decidable. If you want to see all the details, there's a very comprehensive book by Matt Vehef where he explains this. And you can try to do something similar as in the previous slide, which is trying all the possible rider master moves up to some bound. And if you can show that that a certain number of rider master moves will always work, then it gives you an algorithm. And the best bound for this number of rider master moves is this bound here. So make no mistake, this is a big number. Like this C is a big number. That's the basis of this exponential, and this exponential is the height of this tower of exponentials here. So this is not really a practical algorithm, I would say, and so this is close to the best that we can do. Actually, we can do a bit better. So using geometrization, Kuperberg provided an algorithm that is elementary. So elementary means that it's likewise it's a tower of exponentials, but it's only a tower of exponentials of constant size. Also, the constant is not known. So in any case, these are problems which seem to be, from a theoretical perspective, very, very hard. And so it's very frustrating for a computer scientist to see that there is no single lower bound known for that. So it's unknown whether that's NP-hard, let alone X-hard or NX-hard or anything like that. So there's really a wide gap between the upper bound and the lower bounds for this one. And let's just, to finish this this tour, let's just look at a third problem, which seems to be even harder. So that's something that is called the unknotting number. So now I give you a knot, and I want to compute the minimum number of crossing changes. So a crossing change is what's pictured here. You have here a strand that goes above, and you make it go below. Well, no, it's here. Here the strand goes above, and now it goes below. And want to compute the minimum number of crossing changes so that the knot simplifies into a trivial knot, as we see on the right. So here in this example, the unknotting number is 1. And something that is a bit subtle in this definition is that when I do that, I'm allowed to do crossing changes in any diagram of K. So if I give you a given diagram, maybe the best way to do a crossing change is not to work in this diagram, is to use a completely different diagram, do one crossing change here, and maybe this will completely simplify your knot. And so because of this fact that you're allowed to do that in any diagram of K, it's not even known whether the problem is decidable, because there's no finite space that we can search for. Naively, the diagram needed to simplify the knot could be arbitrarily more complicated than the one we started from. And really, even if you're looking to decide whether the unknotting number is 1, so even if your question is there a single crossing change I can do to simplify my knot, there's no known algorithm for that. The problem is not known to be decidable. And likewise, there's no lower bound either. So it's a striking example of a problem for which we don't know whether it's decidable, and we also don't know whether it is NP-hard. And I think that's a sorry state of affairs, and that's why I've been trying, so in the past few years, to figure out lower bounds for problems in knot theory and try to help to improve our understanding of these kind of problems in knot theory. So there are some results that were known prior to our work. So the mother of these results come from a paper of Arnaud, Haas, and Thurston, who perhaps was the first to study lower bounds for problems in knot theory. And they proved that the genus of a knot is NP-hard to compute in a 3-manifold. So the genus is the minimum genus of a surface that has the knot as a boundary. So for example, if you have the trivial knot, it's the boundary of a disk. So that has genus 0. Here we have a picture of another knot and a surface that has this knot as a boundary. And one can see that this surface does not have genus 0 if you compute it. So that's another quantity. So, and computing the best value of such a surface, that was proved to be NP-hard. And there's something else, a more refined notion that was proved to be NP-hard by LIGM, but let me not delve on it. And also, I just wanted to show a few pictures to say that in a previous line of work, basically we observed that these Borromean rings, as I told you, whenever you remove one of them, the rest is unlinked, the rest unravels. So basically, from a computer science perspective, you can think of this like a SAT instance. A SAT instance is you've got a clause, and when one of the variables is true, the clause is satisfied. So basically, these Borromean rings, you can use them to encode some satisfiability instances. And we did that in a previous work to show, for example, that if I give you a complicated some link and I want to find a sublink in there that is trivial. So for example, I want to know whether there's a 4-component trivial sublink in there, that's NP-hard. And basically the idea is what I just said, that Borromean rings encode SAT instances. And likewise, you can compute something a bit similar. You can define something similar to the unknotting number, which is the unlinking number for links, and prove that it's NP-hard using these kind of diagrams. And we had a more complicated reduction showing that finding the best number of Reidemeister moves to simplify a knot is also NP-hard. And I should also say that some other invariants are known to be NP-hard, but I won't delve on that because they're not that elementary. Even defining them is not that easy if you're not used to knot theory. So that's just for the experts. So John's polynomials and coloring invariants are also known to be NP-hard. So let's go back to the crossing number. So I talked about upper bound for many problems. What is the best known algorithm for the crossing number? Well, it's the stupid one. What is it? If I give you a knot that is given by a diagram, how do I compute its crossing number? I try all the possible diagrams with less crossings or as many crossings as the one that has been given. For each of them, I run the algorithm from here with a horrible tower of exponential complexity to see whether that's the same knot or link as the one that was given as an input. And I conclude if I found something better. So that's really complexity-wise something very bad. And prior to our work, it was unclear that it was even NP-hard. There's this quote by a nice survey of Lakenby where he says, well, it's unlikely that there's anything better. But well, this is not a proof. And so we make a small progress on this by proving that this is NP-hard in the setting of links. Once again, for knots, we don't know how to prove it. So let's see a bit how this works. So one can do that very naively first. The naive way to think about this is, well, there's a very close problem that is known to be NP-hard, which is crossing number of graphs. I give you a graph, it's non-planar, and I want to compute the best way to draw it into the plane, which is the one with the minimal number of crossings. So that's a well-known problem, and that's a problem that is well-known to be NP-hard. And so the naive hope would be to reduce from a graph to a link so that you maintain this crossing number. So in order to do that, you can try to do the following. That's really the first thing to try. For every vertex, you replace it with a small unknot. For every edge, you replace it with a small unknot that links the two vertex unknots like that. And then perhaps in your optimal graph drawing, you had an edge that was crossing another edge here. And now the crossings, likewise, are like this. And this seems to be a pretty good reduction. Like the crossing numbers, basically up to a fixed additive factor that will occur at the vertices, they're maintained by this reduction. So the issue with that is that, well, something we used there is that basically prior to doing the reduction, we fixed the cyclic ordering of the edges around the vertex. And when this cyclic ordering, when this permutation is changed, then suddenly your knot is completely, or your link here, it's completely tangled up. Like you cannot permute these edges or these unknots around the middle unknot without them running into each other. So basically, we started with a solution to do the encoding. And there's something a bit more annoying, which is that, well, you also need to prove that the best layout of the link will not cheat. And for example, it could cheat like that. Maybe the unknot in the middle could stretch a bit so as to start crossing other things. And then if the small unknots that were supposed to correspond to the vertices start stretching all around the place, it's not clear how to associate a diagram of a nice drawing of the graph to these things. So out of these two issues, the first one will be easy to solve, and the second one will be annoying, even in our reduction. So let's see how to deal with the first problem. The way we did it is by reducing from a very constrained variant of the crossing number, which is the following one. The input is you've got a bipartite graph like this with two partitions U and V, and below everything has degree 1, above everything has degree 4, and the order of the vertices below is fixed. And so the only thing that moves is the vertices above. Like the degree of freedom of the problem comes from the permutations that describe the vertices above. And this is where you encode the NP-hardness of the problem. And so the nice thing about that is that in contrary to the previous example, the permutations of the edges around the vertices, they're fixed here. It's always the same one. Really, it's only the only permutation that matters is the order of things on the top partition. And so we can transform that into a link using this complicated drawing. So what is going on here? Well, basically you've got a huge frame that is displayed in black and in blue. And the things that move are the red circles here. And the crossings, the edges that were connecting the bipartition here, now there's these green things. And so the way you should think of it is that these red circles here, they're the things that move. Like this one, it can move below this one can move below this one, so they can start moving like that. And in this way, they have exactly the same degree of freedom. This permutation, they can encode this permutation that was corresponding here to the placement of these three vertices. And one can see that if you start from any nice bipartite drawing of the graph on the previous slide, you can naturally get a diagram for this complicated link where the number of crossings will be directly related to what is going on the other side. So that's it. One direction is immediate, and now we need to care about the other direction. And here, I'd like to insist that we've got basically the same issue as before. That maybe here, what we said is that we would really like this red thing, this red unknot, to look like that. But perhaps in some optimal diagram of the link, it will stretch out, and then we don't know what it will look like. So what we need to prove stuff like the fact that everything is rigid. It's as we would expect. And the way we prove it is by proving first that the outside thing, the frame, is a rigid thing. And then this rigidity from the frame will mean that the only thing that can move will be the red curve, and this will be fine. And basically proving that this frame is rigid, you can do this by hand using only linking numbers. As we said, linking numbers, they tell you that basically the top node here will be forced to cross the, let's say, the left node here. So you have these crossings and they have to be there. And you figure it out a bit, you work a bit, and you realize that all the crossings that are pictured on the right, they come from linking numbers. So they all have to be there. And so the frame basically has to be like that. With some work, you can prove that. But of course, so that means that this picture by itself, it wants to look like that. But the second you start adding some new stuff, maybe to minimize the crossing number of the whole picture, then this frame that was very rigid will want to deform. And I will just, before concluding, explain the one issue with that and how we deal with it. The typical way people deal with this problem in graph crossing numbers is that they use weighted crossings, which is just saying, well, whenever I have one edge, I can replace it, let's say, with 5 edges like that, and say that's a edge with weight 5. And basically, if my frame like that, it was done with a very high weight, then it would not want to cheat and stretch out, because the fact that it's got very high weight will mean that any kind of crossing that it's doing would cost you a lot. And so in an optimal solution, this kind of crossings will not be there. So having big weights, having multiple copies of each node basically will be used to enforce rigidity. And there's just one issue here, which is that nodes, they might self-cross. And basically this complicates this kind of reduction, and this makes the argument that we want to carry out significantly harder than what we would be doing in the case of just arguing with crossing numbers of graph. So I will not delve into details because I'm running out of time, but so that's the one subtlety for which we need to be very careful about, and for which there's a solution which involves using a different notion of equivalence for our links. So let me jump to the conclusion. So I think the main open problem I'd like to highlight is that this doesn't work for nodes. Our argument throughout is using linking numbers, which make no sense for a single component. So really nothing works. And for a single node, it seems very hard to figure out any kind of lower bound. And I'm curious to see what can be said about that. It's also open if you fix the value of the crossing number, whether that's NP-hard. So can I test whether a given node or a given link has crossing number 3? That's open, whether that's NP-hard. Then, of course, there's all these egregious gaps between the lower bounds and the upper bounds in the main node theory problems I highlighted before. And I guess I will stop here. So Thank you.
Thank you very much, Arnaud.
Thank you.
All right. Are there any questions? Maybe people are shy, so let me